Hey guys, welcome back to another LeetCode tutorial. In this video, we are looking at problem number 108, that is to convert a sorted array to a binary search tree. This is of easy difficulty and it has been asked by companies like Amazon, Microsoft and Apple before. So let's try and understand the problem statement. It says that you are given an integer array called nums where the elements are sorted in ascending order. So the parameter nums has integers sorted in ascending order. We need to return or convert this nums array into a height balanced binary search tree. So based on this input, you need to return a binary search tree. So now let's try and understand what a height balanced binary tree is. So if you read the definition, a height balanced binary tree is a binary tree in which the depth of two subtrees of every node never differs by more than 1. Okay, so what does it mean? Like if you take a look at this example 1 here, we have 3 nodes on each side from the root, including the root and the left subtree. We have 3 because for us to get from the leaf node to the root on the left side tree, it takes 3. It has 3 nodes. So minus 10, minus 3 and 0. So including the 0, the depth is 3 on this side. Similarly, it's the same on the right hand side. So 0, 9, 5 or 5, 9, 0. The depth on the right hand side is also 3 including the root. Now imagine the same tree not having 5 in this case. So it's the same tree, and then if you remove 5, it's still considered as a height balanced tree because the left side's depth, which is 3, and the right side's depth, which will be 2 in that case, is the difference between 3 and 2 is just 1. So it still falls under a height balanced binary tree definition. So the difference is not greater than 1, right? So that's how that is what is called as height balanced binary tree. So we have our nums array here. Okay, so what are we going to do here is let's imagine this array that we have is like a chain or a string of pearls. Okay, so let me draw something here for you. So imagine we have like a string of pearls. Okay, and then let me draw 5 pearls, and then this is on a table. Okay, now I'm asking you to pick it up and hold it. You can hold only one pearl. Just hold it with 2 fingers. You should hold it in such a way that the pearls on the left hand side of the holding pearl and on pearls on the right hand side of the holding pearl should be equal. So when you hold it up in the air, it should look something like this, right? So you're holding it and up in the air, due to gravity, it should look like this, like a tree. Okay, and then you're holding this one. So that is only possible when you hold the third one, because that is the mid pearl. Okay, so this is the logic that we are going to use also on the array element. Okay, so we have an array. Since we are building a tree which is height balanced, that means we are striving to achieve that the nodes on the left side of the root of the binary tree and the right side of the binary tree are equal in number, or at least they have the same depth, or a depth which is with a difference of just 1. Okay, so that is the goal. All right, I'm just going to get rid of this example, and then now let's start working with the array that we have. Now that we agree that we need to calculate the mid first, I'm just going to do the same thing here. So I'm going to come up with a formula to calculate mid. If you are familiar with binary search, the way we calculate mid using binary search is L plus R minus L divided by 2. What does it mean? So L is the leftmost element index and R is the rightmost index. So left plus R minus L by 2, or left plus R by 2 also works. Okay, so this is how we are going to be calculating our mid. All right, let me put it somewhere here on the very top. Using this, we are going to every time you find a middle, we are going to start building our tree. So in the first case, okay, let me start off here. So we have our array here. The left will be 0, our right will be 4, because nums, there are 5 nums. So 5 minus 1, nums dot length minus 1, which is 4. And then what are you going to do? The next thing that we do is we need to calculate our middle. Middle will be 0 plus 4 minus 0, which is 4. 0 plus 4 by 2, that is 2. And then so that means whenever you find a middle, so you found the node value, because node value will be nums of 2, that is 0. Okay, we found our first element that needs to go get into our binary search tree. So that means I'm going to be creating a node here with 0 as its value. Wonderful. Now let's get going. Now what do you do? So you need to perform the same set of actions. Okay, let me highlight something here. So our mid is this, current mid is this. Okay, whenever you are calling this in recursion, so you first try to build out the left side of the root. Okay, so the left subtree. Now what happens is during the binary search, building the binary search tree, whenever you're looking to the left side of the middle, you need to update your right. Your previous right was at 4, so you need to update that to the current middle minus 1. Okay, in the next recursion. So I'm just going to copy everything and then get rid of this. And what should happen now is our left will be 0, but our right will be our previous middle, which is I'm just going to say previous middle minus 1, that is 2 minus 1, that is 1. Okay, so that is going to be our right. The next thing that we are going to be doing is calculate our middle. Middle is going to be 0 plus 1 minus 0. 1 minus 0 is 1. 0 plus 1 by 2, that is 0.5. But we need to, let me add it here. We need to do math.floor so that we don't have any decimals within our index. So it's going to go to, if it's 0.5, it will be just 0. Okay, so it's going to be 0. Now our node.val will be minus 10, because minus 10 is in the first index of the array, which is at 0 index. All right, so this is our left. Okay, now that we found out a left node, we are going to go ahead and create it. Okay, so we have a node called minus 10 here. The next step is we are going to continue, make another recursive call and then continue. So in this case, I am going to get rid of everything again. So my current left is still going to be at 0, but my right will be previous middle minus 1, which is my previous middle is 0. Minus 1 will be minus 1, which is out of bounds. My array, my index check will go out of bounds if I do array of minus 1. That means my L is greater than R, my left is greater than right. In this case, I'm going to just do return null. Okay, because I have already hit my leftmost value. Then the control is going to come back to node value minus 10. So I went left and here it's just going to be null. Now I'm back at minus 10. So I need to check for my right values. Here what will happen is I'm going to copy this again. So whenever you are doing a write, okay, so again we have the same array. Now instead of going checking for the left side, we are trying to build out a node on the right hand side. In that case, what happens is, so far whenever we are going left, we have been updating our right value But now that we are going to the right, we need to update our left value. Our left value will be previous middle plus 1. So here our right value was previous middle minus 1. Here it's going to be previous middle plus 1. Okay, and then that is going to be our previous middle is 0. Our new left will be 1, and our right will be the same. Right is going to be 1. In this case, left and right are same, so our middle will be 1 plus 1 by 2, that is still 1. And then our node val is equal to minus 3. Here both L and R, left and right, are equal. That is still a valid case. It's not like left is greater than R. That means you found out a middle here, and it's not out of bounds. So node nums of 1, right? Node dot value, you always calculate nums of 1. Node dot value is basically nums of m, right? That is minus 3. Here similarly which will be nums of m, that is minus 10. Okay, so this is what we have. Now let me just color code this differently. Okay, all right, so you are able to get to the right node in this case. So I'll just add minus 3 here. Alright, now that we are at minus 3, we need to check for our left. So our left will be, so what are we going to do? You are going to continue with this. So whenever you are doing a left, again remember what we have been doing so far. So our left is going to be, since you are trying to build a left subtree, our left is going to be our previous left, which is 1. And our right will be our previous middle, which is 1 here, and then it's going to be let's do PM minus 1, which is our 1 minus 1, that is equal to 0. Now we are again hitting this condition of L is greater than R, so you just return null. Okay, and this is basically we have computed a left side for minus 3, so the left side check will be color coded to green again. Now what are we going to do? I will be using another check here, that is we have already returned null from this point. Now the control goes back to minus 3. Now this time I'm going to do a check on the right hand side. So as usual, let's just clear up everything. Now we are going towards right. So when you are going towards right, we need to update when we are trying to build out a right subtree, we need to update our left pointer to previous middle plus 1, that is our previous middle is 1 plus 1, that is equal to 2, and then our right remains the same, which is 1, and this time our L is again greater than R, so you just return null from here as well. That means you just return null, and then the control goes back to minus 3, and then you just return further and go back all the way up to 0. Okay, because these calls have already been done, so the recursion will just keep on returning it, return, and then it will go all the way to the root. Now what happens? We'll have to check for the right of the root. So that means I'm just going to copy this and put it right here. So let me get rid of everything. So the nums is equal to the same nums that we are passing. So since we are computing the right hand side, we are trying to build a right hand side node, our logic is to upgrade our previous middle, right? What is our previous middle? Plus 1. So our previous middle is 2, so it's going to be 2 plus 1, that is 3. Okay, and now our right will be What is going to be our right? Right is going to be the same, which is 4. So we calculate a middle, which is going to be 3 plus 4, which is 7 by 2, that is 3.5, and our floor will be 3. Okay, and now the node dot val will be equal to nums of 3, that is 0, 1, 2, 3, that is 5. Okay, all right. Now we found out the middle, and then which is not out of bounds, and we also found out the value there, which is 5. Now since it's like a right hand side, I'm just color coding it in red. And what are we going to do? Since we found out this, we are just going to draw out our new node onto the right hand side. Now we are going to be calculating the left of 5. In this case, our array will be same again. Our left is also going to be same because we are trying to build out a left node to our current node. So our left will be just 3. Our right will be previous middle minus 1. Okay, and that is equal to our previous middle is 3 minus 1, that is equal to 2. And then this time our L is greater than R, so you just return null. Okay, so this will be null. Now what should happen is we need to calculate the right. Now that we are calculating a right to this tree, to the node 5, so we will be starting off with our L, which is going to be our previous L. And actually our L will be PM plus 1, previous middle plus 1. So it will be our previous middle is 3 plus 1, that is 4. And our right will be the same as previous right. The middle will be 4 again, because 4 plus 4 by 2 is 4, and node dot val is equal to nums of 4, that is equal to nums of 4 is what? 9. Okay, we found out our other node, which is 9 to the right hand side. Now we are just going to if we check our left and right hand side here, we are going to hit our null value. Since we are calculating our left is going to be our previous left, right is going to be previous middle minus 1, 3. So we have hit L is greater than R, so you just return null, and then this is going to be our left subtree. Similarly, we are going to be having our right values. Since our previous is 4, so it's going to be 5. Our R is going to be 4. Our middle is we cannot calculate middle because L is greater than R, and we just return null. So both the child nodes for the 9 will be null and null. So, and then you just return back, and you are going to return the top level node, which is 0, and then you will have the entire tree built up. So that is how you are going to be working on this problem. I know this explanation was long, but I just wanted to help you understand each and every step of the stack trace. When we are building, or when the recursive calls happens, this is how each state of the recursive call looks like. So that's why I'm just going to add a few boxes to these call stacks here, so that you will understand exactly the tree representation of these calls. So this is how it looks. So you can just compare this as a mirror image, right? Like you're just comparing it with how our tree looks like. So this is exactly our call stacks, and every time you get a node dot value, you will have a corresponding value on the right side of the tree. Okay, I hope this is clear. I know it's a lengthy explanation, but I really hope that you understand this and you found some value out of this explanation. So I'll just go back and let's code up the solution. Okay, the first and foremost thing that we are going to do is if nums.length doesn't exist, that means it's a the nums array is 0. So you just return null as our the answer, right? The answer will be null, and you can use a function here called convert to BST, and then you just can return convert to BST. Here you need to pass in a left and a right, so that will be this one 0 and nums dot length minus 1. That's the first call that we are going to make on the very top. So it will have L and R. If L is, this is our base condition to get out of the recursive call. So you just return null. Otherwise, you are going to create a node with a new tree node with the middle value, right? So what you do is you need to calculate middle equal to math.floor of L plus R minus L divided by 2. So this is going to give us the middle. Once you get the middle, you just need to do nums of middle. That will take care of creating a right node with a right value. Then all you need to do is you build that and you start building the left and right subtrees. So this is going to be a recursive call. So when you do left and then when you do right, we already spoke about it at length, the formula, right, to update the left and right. When it's left, you're going to do middle minus 1 as the new right. When you're going right, you're just going to do middle plus 1, and then you're going to have the left as the same here, the right will be the same. Finally, you're going to return the node. So just to repeat it, so we calculate middle and then we calculate the node, and then you start building the left subtree. When you start building left subtree, your L is going to be the same, but your right is going to decrement by whatever the previous middle was, and then you call it recursively until you hit null, and then once you are done building the left subtree, again you do recursive calls on the right hand side, which makes where L will be middle plus 1 and our right will stay the same, and again it's going to hit L greater than R at one point. If L is greater than R, you will hit the leaf node, that is, and then you'll return null. After that, you finally return all the recursive calls, and you just return the top of the node, which will give us the entire tree. I hope this will work. So let me just go ahead and run this solution first. So as you can see, my output is 0, minus 10, 5, null, minus 3, null, 9, which is different from this, but it's still accepted because there are two ways how this tree could be built. So the one that we were able to build with this code is this one: 0, minus 10, minus 3, 5 and 9, which is similar to whatever we have without the nulls, right? So yeah, this is still an accepted solution, so it passes for case 1 and case 2. So I'm just going to go ahead and submit this. So this has been accepted, and that is how you solve this problem of converting sorted array into a binary search tree. I hope this explanation has added some value to you guys. If you like my explanation, please give it a like. and consider subscribing to my channel. I'm going to be posting more videos, or I'll be solving more LeetCode problems in the coming tutorials. Thanks again for watching. I'll see you in the next one.